Hey guys, example 2 here, and because I did a lot of hand holding in example 1, I'm not going to do the same kind of hand holding here. But yeah, obviously I'll tell you all the important details you need to know to fully understand this video. Now, first, in this video, we're dealing with sine of x, the function sine of x. Whereas in example 1, we dealt with the function e to the x, right? Okay, cool. And the next video will be cosine. So here, it's sine x is f, and the Maclaurin series for sine has for all functions is written up here. And I remind you that this here means the nth derivative of f evaluated at 0. So when n is equal to 1, we mean the 0th derivative of f evaluated at 0, but the 0th derivative of f is just f itself. That's before we took any derivatives. So this here is just f of 0, hence why you don't see like a 0 written right there, because it's same as f of 0. F of 0 is same as this. Yeah? Okay, cool. But otherwise, the rest of them are pretty self-explanatory. When n is 1, we need f prime of 0 up here. That's what this will mean when n is 1. And then when n is 2, f double prime of 0, and so on and so forth. Yeah? All right, cool. And when you see what's written here, curiously, you'll see a lot more derivatives written out than we had to for example 1 of the function e to the x. And you'll see why we have to write so many derivatives for sine x. But think about why, like once you see what I've written here. Yeah? Okay, cool. And I'm going to answer it shortly. Answer why we need so many derivatives here. All right, cool. Now, equally importantly, this ... right there is crucial because sine x equals this only as an infinite sum. In other words, if I change this to a finite number, then we won't have sine x exactly. We'll have a really good approximation of sine x when this is finite. But yes, we need it to be infinite in order for it to equal exactly sine. Yeah? Okay, cool. Otherwise, I think we're ready, right? This here means sine of 0, and sine of 0 is 0. So we have, right now, since sine of 0 is 0, we have 0 over 0 factorial. Yes, I can write 0 factorial as 1, but I'm intentionally writing it 0 factorial. And then, of course, we have this times x to the 0th power, right? And that x is supposed to be in blue. So we have this times x to the 0th power plus, and then this here is the first derivative of sine evaluated as 0. That's cosine of 0 then. Cosine of 0 is 1. So we have 1 divided by 1 factorial, and then times x to the first, right? Times x to the first, and then plus, and then you get it. This here is going to be negative sine of 0. That's negative 0, but that's still 0. So we're going to get 0 over 2 factorial. So do you see why we needed so many derivatives? Because we're writing the first so many terms here so that we can figure out the general terms that we can write somewhere out here, like more generically, right? Hence the general term. And we won't be able to figure out that general term if we just write 5 derivatives and then most of the terms are going to drop out, right? Like this is going to be 0, and this too is headed to be 0, right? But yeah, let me first write what's multiplying this, which is x squared, right? Okay, x squared is multiplying this, right? And then plus the third derivative, right? This evaluated at 0 is going to be negative cosine of 0, and that's negative 1. So we'll get negative 1 divided by 3 factorial, and then it will be times x to the third, and we're going to keep adding terms, but you know, I need the space, so let's get rid of all the terms that drop out. So this drops out because it's 0, and this drops out because it's 0, right? Okay, so took too much, a bit too much. Okay, and so let's scoot these guys closer, right? Okay, and like move them closer to the equal sign. And now if I continue in this pattern, it's pretty clear that the fourth term is going to drop out because I'm going to get sine of 0 again. So what's going to survive is this guy, right? the term involving the fifth derivative. I shouldn't even say the fourth term for this guy because it dropped out. Technically, the next term we write, which is about the fifth derivative, is actually the third term of our series, right? Okay, cool. But yeah, that's going to be cosine of 0, which is 1, divided by 5 factorial times x to the fifth, right? Okay, times x to the fifth. And then plus, the next one is going to involve, well, again, this is going to drop out. And so the next one is going to involve the seventh derivative. And that's going to be negative cosine of 0, which is negative 1. And then divided by 7 factorial, right? So this divided by 7 factorial. And then times x to the 7th, right? So times x to the 7th. That's supposed to be in blue. My bad, y'all. X to the 7th. And then plus dot, 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 right? Okay, it's an infinite sum. We need that. Okay, I think we have enough to determine the general term. We've got 4 terms here, and that's sufficient for us to establish the pattern necessary for the general term. And this is what it is, right? And this is what it's got to be. First, you see that because we're going 1, negative 1, 1, negative 1, we need negative 1 to a power, because that's how you're going to get alternating terms like this. So we need, let me write a blue plus sign. So plus, that's not blue. All right, blue plus sign. And then we need a negative 1 to a power, right? Negative 1 to some power. What power is that? Well, we'll worry about that in a second. We'll worry about what exponent negative 1 needs to have. But let's cherry pick the easier stuff. These are all just the odd numbers factorial. We know that we can write odd numbers in closed form as 2n plus 1. So it's just 2n plus 1 factorial, right? Okay, cool. And then, of course, we need to multiply this by x to what power? Well, let's see. This 3 and that 3 correspond. This 5 and that 5 correspond. So it's pretty clear that we need to have this and this exponent correspond. So we're going to have 2n plus 1. Okay, we've done all the easy stuff now. And so let's figure out the exponent on negative 1. Okay. When n is equal to 0, right? Because, yes, Maclaurin series can start at like n equals 1, but like you still need to count in consecutive integers, right? Like sigma isn't going to skip count for you. If this is n equals 1, the next one will be n equals 2. So if this is n equals 0, the next one will be n equals 1, and then n equals 2, and so on. So this actually corresponds to n equals 0, right? And so does this give us 1 factorial when n is 0? Surely it does. Look at this general term. When n is 0, we get 2 times 0, which is 0, plus 1 factorial. So that's 1 factorial. And then the exponent is also going to give us this exponent of 1. Great. But on this negative 1, we needed to turn into a positive 1 somehow because this term is positive, right? And we're plugging in n equals 0. Well, I think if we plug in a 0 right there, if we put a 0 right there for n equals 0, then it would work. So maybe our first guess is n right here, and then we'll adjust if that's not correct. So right now, this n is working because negative 1 to the 0th power is positive 1, and we'll get that positive term here, right? Okay, cool. And of course, as we saw, we have all the other parts to this in this general term, right? Okay, cool. Let's check it on the second guy. On this guy, remember, it corresponds to n equals 1. This was n equals 0, so this corresponds to n equals 1. And when n equals 1, this is surely going to say negative 1. Good. And then this is going to say 3. Good. And this is going to say 3 factorial. Good. What about the next term? Are we good here? Yes. And remember, this corresponds to n equals 2. When n equals 2, that'll be 2, so we get negative 1 squared, and that's positive. Good. And then this is going to be 2 times 2 plus 1, which is 5 factorial, and that's good. And obviously this is good. Okay, now you can check it yourself, but all I have left to do is write plus dot, 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 and then I'm done in the term-by-term rewriting, and the term-by-term writing of the Maclaurin series for sine. That was too close for comfort. Okay, plus dot, dot, dot. Yeah? Okay, cool. And as always, I'm going to help you write sine in its closed form. So we can write sine x, and its closed form as, and closed form is like when you're using sigma, but we can write it as n equals 0 to infinity, and then all we have to do is write the general term here, and I'll do that in black because I want to do this quickly. The color coding takes a bit of time, but yeah, x to the 2n plus 1, and then all of this divided by 2n plus 1 factorial, and we're good. Yeah, cool. Now, in the next video, I'm going to do the Maclaurin series for cosine, but I'm going to do it by cheating. In other words, I'm not going to reinvent the wheel and show you how to do it this way. As you can see, this is a very tedious way to find Maclaurin series of functions. But it is a way, and it's like the way, right? But we can also cheat and find Maclaurin series very efficiently, and that's what I'm going to show you in the next example. And I won't tell you how here because, yeah, cliffhanger. Yeah? Okay, cool. Last thing is, you know, as I said over and over, this ... is crucial. Because, again, this infinite sum equals sine x only as an infinite sum. So if I were to, like, you know, get rid of all the terms beyond the x to the 5th term, then I can, but I can no longer have an equal sign there. What I get is a very good approximation of the sine function. Isn't that really cool? You can approximate the sine function for values around 0 very well by just that. Yeah? Okay, cool. And so that's one reason why Maclaurin series are helpful. They give us approximations of like crazy functions in a local area. All right? Okay, cool. Like I said, next example is cosine, and more examples to come. To be specific, we'll go all the way to example 7. Keep watching. Thank you.